Hi everybody, welcome back to the video, or to the channel. In this video we're going to take a look at something called optimization. And optimization is just kind of a fancy word for saying find the maximum or the minimum of something. So to start out, we're going to kind of look at an example, and then we're going to walk through some steps about how to be able to handle problems that are asking you to find a maximum or a minimum of something. Now that we know how to do that using some calculus, let's look at some practical real-world application problems. Now, the best thing I can kind of relate this to is when we talked about related rates. And so, if you remember related rates, we started out with a word problem, and we tried to be able to bring that into looking like math, and then solving the math problem, and then express our answer back in terms of the context of the word problem. And optimization is going to be pretty similar to that. Now, I think there's a little bit more of a structure that works nicely with optimization. That's a little bit more refined or exact than related rates, but and so that's a good thing. But it still is very, very similar, and so we still need to be able to interpret some problems. Let's take a look at this first problem, which is probably one that you've seen before in a different class and be able to handle in kind of a different way depending on what kind of a context or what kind of a class that you're in. Okay, this says that a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, so in this problem, I don't know if you hear any idea of a maximum or a minimum, but I kind of hope you do. And the more problems we do of this, the more we're going to be able to pick out the wording that talks about a maximum or a minimum. So when it says, what are the dimensions of the field that has the largest area, another way to think about that is we are supposed to maximize the area here of the field. All right, so first of all, I think what's helpful in these, and this is going to be one of the steps that we see in a minute, is it's helpful to draw yourself a picture. So here's my straight river, and we have fencing, and we want to fence off, it just says a rectangular field. So I don't necessarily know whether the one side here is longer than the two that are on the other side there, kind of along the river there, or if it looks more something like this. I don't know. All we know is it's supposed to be a rectangle. And so since we don't know, and we don't know what these dimensions are, that's what we're trying to find, let's go ahead and give these labels. And we're probably going to call these X and Y, or call them kind of whatever you want there. And you probably in your past have some kind of a method to be able to deal with this and figure out kind of what is it that that we can find in this problem in particular. And that's because this problem ends up being a quadratic. And so from your past, if I said, here's a quadratic, can you find the maximum of that quadratic? That's like saying, can you find the vertex? And so you should probably be able to do that from past classes. Now, in this section, we're going to look at other examples that are not just quadratic examples, where we can go and we can still find maximums and minimums now using calculus, not just because it's a quadratic example. But let's kind of look at what we would have done in this case. We know that we have 24 feet of fencing, so you would have said something like x plus 2y is equal to 2,400, because that's how much fencing we have. And it says we're looking for the area, and so area is equal to x times y in this problem. And what you might have done in your past is you would have probably taken the top equation and solved for one of the variables. That's going to be something that's really helpful for us in our in kind of our steps in this section. So my suggestion would be to solve for x. So x equals 2,400 minus 2y. And then what you might have done in your past is substitute in for x. So a is equal to x times, or actually we're replacing for x, aren't we? Because x is solved by itself. So it's x, which is 2,400 minus 2y, and then times y. And here's why we can find a maximum in this problem, is because when you distribute the y here, you get 2,400y minus 2y squared. So what you know is that this is a quadratic that opens down as far as the area function here. So when you know that this is a quadratic that opens down, saying could you find the maximum area? Well, that's just finding the vertex of a quadratic. Here's the thing, now we know how to be able to find a maximum and a minimum in a bit of a simpler way rather than just finding the vertex. and that uses derivatives. So you could go and you could say, let me find the derivative of a, and when I find the derivative of a, could I use that derivative to find maximums and minimums? So you might go from there and you might say, let me find a prime, and a prime looks like 2400 minus 4y. Well, how do you find maximums and minimums? Those are critical points. And so you look at, where is a prime undefined? Nowhere, actually, because this is a linear function. Domain is all real numbers. And then the other thing you should do with that is set that equal to 0. And so if you set this equal to 0, you're going to get 2400 equals 4y, and then divide both sides by 4, you get y equals 600. And then you can plug back in and find what x should be. We are trying to find the dimensions, so we need to find both x and y. We have something like x plus 2 times 600 equals 2400. And so, let's see, 2 times 600 is 1200, so subtract 1200, you get x is 1200. And so, these are the dimensions that maximize the area. Again, this is probably a problem that you've seen before, but the idea is that at some point we have to get a function by itself, a, that only has one variable in it, that only has a y. Notice at the beginning we had an a that had an x and a y in it. That was a problem. So we had to do some substituting, and then when we had an equation for a that just had one variable in it, then we could either use the vertex formula, because we know this is a quadratic, or we could, what we're going to do in here is we're going to take the derivative and use maximums and minimums, and in the way that we've been doing in the last few videos, and find, in this case it's going to end up being the maximum area. Okay, we should probably test that and just make sure that it's the maximum area, that we didn't get like a minimum area or something like that, because sometimes there could be more than one critical point, but in this case we're going to be okay. There's only the one point to be thinking about, because when we solve this linear equation there's only one value for y. So in this problem we're okay, but in general it is good just to check, did we get the maximum or the minimum that we were looking for? So let me kind of lay out some of the steps. Let's kind of recap what we did. I have 8 steps that kind of walk us through how to be able to deal with an optimization problem like this. And it's kind of similar, again, to related rates, but I think you can almost always follow these 8 steps and kind of use this as a general structure for your problems. So first one, I probably shouldn't have to say this, but read the problem carefully. Make sure that you understand what's happening here. Number 2, it can often be really helpful for you to draw a picture. In the last problem, we had this picture of a rectangle along a river. So just set up some kind of a diagram or picture based on the situation that you have. Okay. Now, really, from here on out, there's going to be 2 things that we're using. One of them I'm going to call the formula, and the other one is going to be called a constraint equation. So the formula is going to be, what is it that you're trying to optimize? And remember, optimize means find a maximum or a minimum. So what is it that you are trying to find a maximum or a minimum of? Okay, let's go back to the problem that we just had. What is it that we were trying to find the maximum of? Well, when it says largest area, that is our formula F that we are trying to, or we called it A here for area. That is our formula that we're trying to find the maximum or the minimum of. So I would start out by looking at the question that you're being asked and saying, what am I trying to maximize, or what am I trying to minimize? Well, that's why the first thing that we did was we said, or I guess you can do these in either order. We said A is equal to x times y, that's our formula. And then our constraint equation, let me go back to our steps. Step number 4 says set up a constraint equation, and that almost always involves a fixed value. Okay, so if we look at the problem, the fixed value that we had was that we have a fixed 2,400 feet of fencing. That's kind of like thinking about the perimeter on the outside. So the fixed value that we have says is 2,400 feet. There should be an equation that we can set up involving 2,400 feet. So for us, that was the equation x plus 2y equals 2,400. So we have a constraint equation, and we have a formula, and the formula is what we are trying to optimize. Okay, so this is steps number 3 and number 4. Set up a formula, what you're trying to optimize, and set up a constraint equation. Then the steps are basically going to walk through what we just did in the problem. If you notice what we did, next is we took the constraint equation that involved the fixed value with x and y, and we solved for one of the variables. That's going to be step number 5. Solve for one of the variables in the constraint equation. And I'll tell you, this is usually going to mean you get one variable by itself and you still have another variable in the equation. Okay, so like in the last one, we solved for x, but there was still a y in there. That's okay. All right, that's good, actually. Most of the time, that's going to happen. Then, step number 6, once we solved for a variable, we substituted back into the formula. So area was our formula over here. We said, hey, if we know that x is equal to 2400 minus 2y, go ahead and replace an x with what x is equal to. And if you replace an x with what x is equal to, or replace one of the variables, what you're hopefully going to have at this point is you're going to have your formula, in this case it was a, that only has one variable in it. Now at this point, a only had a y in it. There were no more x's in there. So, step number 5, solve for a variable in the constraint equation. Step number 6, substitute into the formula. And usually, and I could kind of put a sentence into number 6, usually what's going to happen is that your formula now is only going to have one variable in it. Okay. Now, that is what we're trying to maximize or minimize. It only has one variable in it now. So great. Now go ahead and take the derivative of your formula that only has one variable in it. That's where we found a prime up here. And then after you found a prime, set a prime equal to 0. Or, by the way, we also could, depending on the function that we have, we might need to figure out where does a prime not exist. Basically, we're saying find critical points. And so, in step number 7, I said use derivatives to find critical points of your formula, both where does your derivative not exist and where's your derivative equal to 0. And by doing that, you're going to solve for a value. Now, in this case, we didn't just have a value of y. We actually had to go plug that value of y in and find x as well. So really, a part of step number 7 isn't just it isn't just finding a critical value like one number. Notice it says finding critical points. So critical points having multiple coordinates like an x-coordinate and a y-coordinate, both. So you want to find both of those. So once you've found one value, make sure you plug that into your original constraint equation to solve for the other value of your other variable there. Okay, and then at the end I mentioned this, but it's just a good thing to check for. Number 8, verify that the value you find answers the question. Here's the deal. In this problem, we only had one critical point, but you know that that's sometimes not the case. Sometimes you might have a problem, and depending on the area or the formula that you have, you might actually end up getting 3 different critical points. Okay, and so the question is, out of those 3 critical points, which one gives you the largest area? And so you need to actually go and make sure that you kind of, essentially this is like checking your work and checking to make sure that what you found actually does what you want it to. Okay, if you get 2 critical points and one gives you a largest area and one gives you a smallest area, obviously you don't want to just pick the one that's going to give you the smallest area and say, oh, that was a critical point, it must be it. No, you should actually check your work, check your answers at the end, and make sure that that makes sense in context and is what you're actually looking for. Okay, so probably step 8 probably shouldn't even be mentioned, but I will mention, I will throw that in here just to say make sure that you're actually answering the question. Okay, and then at the very end, I could say, just like with related rates, make sure that you're answering the question in terms of the context of the problem. If there are units in the problem, make sure you use units. Make sure that you're answering using complete sentences. Again, think about this as kind of a business example where maybe your boss comes to you and asks you about a problem, and you turn it into math. You use math and solve the problem, but when you go back to your boss and present your answer, you're not just going to give them the math. You're going to say, here's what I found, and you're going to use your words. You're going to use complete sentences, and you're going to use units that are there that make sense in the context of the problem. So that's probably just a good way to recap your problem. And so here, X and Y are talking about feet of fencing, and so we should say that we should use the picture that we had before that I actually erased, where X is 1,200 feet and Y is 600 feet. And so you should explain that using words. Okay, so we're going to see some examples of this, but this is the main idea about how to handle optimization problems. Hope you've enjoyed.